So guys, as you know that better AI needs better silicon chips, and solar panels also need silicon, but we are super short of refined silicon and other important materials. Now this is a big conundrum if the world aims to move towards sustainability. There is a problem, but now scientists at Google's Deepmind are edging closer and closer to a possible solution. I must say, it is kind of amazing how AI is trying to solve problems standing in the way of its development. Yes, AI is solving the biggest research problems in material sciences. How? Let's find out. Did you know that earlier in the year, a South Korean laboratory unveiled a groundbreaking discovery touted as the holy grail of electric efficiency and a potential genuine answer to the energy crisis? In July, researchers from Korea University in Seoul presented chunks of a gray-black polycrystalline substance named LK99, asserting that these could be amalgamated to create a room-temperature, normal-pressure superconductor. However, these claims did not withstand subsequent scrutiny. But then, a new series of efforts began. Within a few months, Google's Deepmind published a paper in Nature in which the authors presented the discovery of 2.2 million new crystals, equivalent to nearly 800 years worth of knowledge. The paper introduces graph networks for material exploration, or GNOME, a new deep learning tool that significantly accelerates the pace and efficiency of discovery by predicting the stability of novel materials. By using GNOME, researchers effectively increase the number of technologically viable materials known to humanity. Now, why am I saying this? Hey, everyone wants better GPUs at lesser cost. Everyone wants to receive a net zero electricity bill. Everyone wants to wipe fingers over premium materials. And I am not so sure if everyone wants to drive electric cars, but still, we are not there. Normally, finding these new materials is a long and hard process. Scientists spend years mixing and testing different elements, trying to get the right combination that has the properties they want. And even when they find something that works, they might not fully understand why or how to make it even better. This is a true banger because among its 2.2 million predictions, 380,000 are identified as the most stable materials, representing promising candidates for experimental synthesis. These materials include substances with the potential to drive future transformative technologies, such as superconductors for powering supercomputers and advanced batteries to enhance the efficiency of electric vehicles. It is important to establish here that Genome and AlphaFold are often confused because both originate from Google Deepmind and both use deep learning for different purposes. But here is the difference. AlphaFold works on predicting protein shapes crucial for life, made of amino acids that fold in complex ways. Genome, on the other hand, predicts material structures. It focuses on how atoms, the building blocks of materials, and how they come together to form various crystal shapes. Now, before we start talking about Genome again, it is important to mention that Google Deepminds also developed a new tool called Alpha Missense, which can predict the potential harm of genetic mutations. This tool is designed to identify missense mutations, where a single letter is misspelled in the DNA code, and assesses whether they are likely to cause diseases. The project, led by Deepmind engineers Yoon Cheng and Giga Avsets, have resulted in the public release of predictions for 71 million possible variants. The new software, described in a report published by the journal Science, is part of an effort to uncover the root cause of genetic diseases and has been tested by Genomics England with the aim of speeding up the diagnosis and treatment of rare disorders. Additionally, Deepmind has also made significant progress in the development of the next generation of AlphaFold, a model that predicts the 3D structure of biological molecules, including proteins, nucleic acids, and ligands. Now, why did I say AI is solving problems standing in its own way? Well, that is because we are not catching up with Moore's law. If you don't know what it is, in simple words, it's a phenomenon that suggests semiconductors will become twice as powerful every passing year. Many experts still think that we have already exhausted silicon's ability, but some still believe there is much more that can be achieved from sand. New materials are being explored to keep up with Moore's law, but research is also going on to find ways to print more complex circuits on existing silicon-based wafers. A method to grow 2D materials, including 2D crystals, on existing silicon wafers has been developed by researchers at MIT. This advancement could aid in the production of smaller transistors necessary for sustaining the trajectory outlined by Moore's law. A new generation of devices employing 3D packaging techniques is demonstrating notable improvements in power density, providing an alternative avenue for keeping pace with Moore's law. Now, this whole genome project is all about new materials, and this study clearly demonstrates the potential of employing artificial intelligence to explore and develop new materials on a large scale. Independent researchers in laboratories worldwide have experimentally created 736 of these new materials in concurrent work. In collaboration with Google Deepmind, a team of researchers at the Lawrence Berkeley National Laboratory published a second paper in Nature, highlighting how AI predictions can be utilized for autonomous material synthesis. They plan to contribute the 380,000 materials predicted to be stable to the Materials Project, which is currently processing and integrating them into its online database. The researchers anticipate that these resources will propel research into inorganic crystals and unlock the potential of machine learning tools as valuable guides for experimental directions. In the past, scientists had embarked on the quest for novel crystal structures by manipulating known crystals or engaging in experiments with fresh combinations of elements. This process, characterized by its expense and reliance on trial and error, often stretched over months before yielding even limited results. Over the preceding decade, computational methodologies spearheaded by the Materials Project and various other research groups had played a pivotal role in the discovery of 28,000 new materials. Despite these advancements, AI-guided approaches often encounter a fundamental limitation in accurately predicting materials with experimental viability. Among the newly unearthed materials were 52,000 layered compounds akin to graphene, which, if you don't know, is kind of a superconductor. You can Google what a superconductor is, but for now, consider it a bigger, badder brother of semiconductors. Do you know about how many such materials we knew about before this experimentation? Only 1,000. Not only that, the exploration revealed 528 potential lithium-ion conductors, a staggering 25 times more than earlier studies. Okay, you've heard me say stable materials quite a lot of times throughout this whole video, but what actually do I mean by stable materials? Well, they should not decompose into similar compositions with lower energy. To put this in context, consider the ongoing search for solid electrolytes that could replace the liquid electrolytes that are currently found in lithium-ion batteries. As a prerequisite, these electrolytes have to be stable, should have specific conduction properties, while being non-toxic and non-radioactive. Or say, the ongoing work on the new layered compounds, similar to graphene, that could potentially revolutionize electronics and superconductors. Mathematically, these stable materials resided on the convex hull. Wondering how this magical new AI works? Well, let's find out. Gnome employs two distinct pipelines to identify stable materials with low energy. The structural pipeline generates candidates by aligning with known crystal structures, while the compositional pipeline takes a more randomized approach based on chemical formulas. The result from both pipelines undergo evaluation using density functional theory calculations, contributing to the genome database and guiding subsequent rounds of active learning. As an advanced graph neural network, Gnome processes input data in the form of a graph representing atomic connections. Initially, Gnome was trained with openly available data from the Materials Project. It had everything from structures and stability information. The model was applied to generate novel crystal candidates and predict their stability. Through progressive training cycles, they assessed the predictive capability of Gnome using established density functional theory calculations, commonly employed in physics, chemistry, and material science, to understand atomic structures crucial for evaluating crystal stability. Active learning played a pivotal role in enhancing Gnome's performance. The model generated predictions for novel stable crystal structures, which were validated using DFT. The resultant high-quality training data was then incorporated into the model's training process. The research significantly elevated the material stability prediction rate, advancing from approximately 50% to 80%, based on matte bench discovery and external benchmarks set by prior state-of-the-art models. Moreover, this model achieved a substantial efficiency boost by increasing the discovery rate from under 10% to over 80%, potentially reducing the computational resources required for each discovery. Now let's look at some other examples of materials that Gnome has discovered. Subscribe to Innovella for more blues from the world of AI. There are rumors that Sam Altman was fired because he was working on some kind of an AGI. I simply cannot claim to be sure that this was the reason, but still, he was working on something super powerful. It is called the Project Q Star. To find out what it is, click on the video links popping up.